In one of the previous slides, we have learned the single layer in metallic crystalline, which is like either they are square or they have this hexagonal structure. So to make the three-dimensional like this, what we do is, or not we actually, but I mean, to understand the concept of is that we stack this layer. Yeah, we stack this layer. So for example, here, if we start from the hexagonal two-dimensional layer, and we stack the hexagonal three-dimensional layer according to ABC stacking sequence. What does it mean? So like this, yeah, the first layer, the A, in the A side is denoted by these green balls, the bottom layer. The second layer, the B, is located, each ball is located just at the space above the bottom three balls. Okay, so you see the green balls here, and there are space in between the three balls. The B, the second sequence on top of these three balls, the ball is located just above it. Okay, then, and eventually similarly with the other balls. So the B layers here, the blue ones indicate the second stacking sequence. After that, C here indicates that the third layer will be located in the space not exactly above the balls of the first and the second layers, but in the space between them. So in this case, C here, the C here is denoted or indicated by the yellow colored balls, the yellow colored circles, is located just above the space, which is not on top of any of the balls, not directly on top of the blue balls or the green balls. Okay, and the stacking, if we see from the different side, then it basically form an FCC unit cell, a face-centered cube unit cell like this. See here, so this yellow atom becomes the one atom in this corner. The A atom, the green atom, becomes the atom on the other corner, and the other corner here also with the green. This is with green. The farthest bottom corner is also occupied by the green A atom. This bottom nearest corner is occupied by the blue atom. Then this one is by the blue atom, the second layer. This one is by the blue atom, while the face, while the position at the center of each face is occupied by, in this case, the blue, and this one is the green, and the green, and the farthest side, respectively. Okay, so the face center cubic that we have just learned in the previous slide is actually made up from hexagonal two-dimensional layer, which is then stacked according to the ABC stacking sequence, which is then put on a certain orientation like this, yeah, such that then the B becomes the layer in the middle. Yeah. So if I ask you now, indicate using Miller indexes, what is the plane that is formed by the B atoms in this FCC unit cell? Indicate using Miller indexes. Can anyone answer? Ezra? Just try. You can annotate the presentation if you'd like, using annotate.
Maybe I'll try that.
What is that plane within that single unit cell?
So for the X is in here. So
Yes.
the shape is like this, right?
Yes.
So it's 111.
Yes,
Yeah.
it is one. It intercepts the x-axis. So let's say, yeah, it is basically 111 family. It is 111 family. Yeah, it intercepts the x-axis in. So let's see. Let me draw. Yeah, this is correct. This is 111 family. Basically among the 111 family plane. Yeah. Where does it come from? So actually the 111 family, the A plane is also in 111 basically. Yeah. So the A plane is in this corner, in this corner, in this corner. This is actually the actual 111 if we put the origin in that way. So, but the B plane is also basically 111. Yeah. But only in different side, different orientation, something like that. Yeah. Okay. So now, so this is hexagonal. This is FCC, right? The previous picture is the FCC stacking sequence where we stack the hexagonal 2D layer into ABC stacking sequence. Yeah, ABC, ABC, ABC. Another way of stacking is when we stack using the sequence AB, AB, AB. So after the first stacking layer A, and we stack the second layer in the space between the first layer, atoms. Then the third layer is stacked exactly above the first layer atom. The third layer exactly above the first layer atom. Yeah, so that is why the stacking sequence is called as ABAB. So like this is the A side. The atom here is located just at the space between these three atoms. Yeah, 1, 2, 3 atoms. Yeah, here. And also this, and then this A side exactly above the first A. The third A side here, exactly above the first A side. This is a 3D projection, and 2D projection will look like this. The coordination number is basically still the same. In FCC is 12 here. We're using ABC stacking sequence. In hexagonal closed spec structure, it is also having 12 coordination number. The APF is also the same. So HCP has the same atomic packing factor as FCC, yeah, 0.74. Only they have different crystal structure. In this crystal structure of FCC, you see that the lattice constant is the same in 3 dimension, in 3 axis, yeah, A. While in HCP, the C is not the same as the A, yeah, the lattice constants. And the C over A, the ratio of C over A is 1.633. And the number of atoms or unit cell is also the same with FCC, which is 6. Yeah, here we have. No, FCC has 4. Sorry, my mistake. But HCP has 6. Because here, if we look at this unit cell, we have 3 in the middle, completely 3. Yeah, 3 times 1, so equals to 3. Then we have this on the face, which is half, right? There are 2 of them, so 2 times half, so equals to 1. And we have this one atom here at the corner is shared by how many unit cells? 6, yeah. So 1, 2, 3, 4, 5, 6. And there are how many? 12 of them. But each of the atom here is shared by 6 unit cells. So this becomes 2. And in total, we have 3 plus 1 plus 2 is 6. We have 6 atoms per unit cell. So example of metal that has that has this HCP crystal structure are cadmium, magnesium, titanium, and zinc. Okay, so let's move to another example of solid state crystalline structure. In this case, now non-metallic crystalline structure, yeah, which is compound. Yeah, this is sodium chlorine. Sodium chlorine basically is the salt that normally we use every day to cook and many things. So this is the structure of sodium chloride. So in the metallic structure, we studied solid, which has basically the same single atom type, single element. But when we have compound, means that we are combining atoms from different types, from different elements. So this is sodium chloride or salt. It comes from sodium and chlorine. And the binding is ionic binding, ionic bonding. Yeah, sodium plus bond with chlorine negative, chlorine minus. So the structure is close back direction along the cube edges. So it's like this. Here, if it is only sodium, it would look like a face center cube. But the chlorine fills in the gap between the two sodium atom, because the chlorine is, sorry, the red one is the chlorine, yeah. The red one, this one is the chlorine, because the negative ion has larger size compared to the positive ion, the cation. The white one here is the cation. So the chlorine here fits into the cube, has center cube, and the sodium then fills in the space between the chlorine. So from this crystalline structure, we can also calculate the theoretical density of that particular solid. Yeah, the density is defined here from physics also, but in this case of material science, we define it per unit cell. The mass of the atoms in a single unit cells or divided by the total volume of the unit cell. The mass of atoms in one single unit cells is calculated by the atomic number per unit cell here, and which we have derived, yeah, which we have shown to you and in the previous slide for different configuration, FCC, different structure, FCC, BCC, simple cubic. And A here is the atomic weight, so the weight per single atom. And divided by the volume of the unit cells. Okay, the total volume of unit cells. The total volume of unit cell. Here, sorry. So the mass of the atoms in unit cells is the atomic weight times the atomic number of unit cells divided by the Avogadro's number. Okay, so this is to find the Avogadro number divided by Na here. The Avogadro number is basically the atoms per mole. So from here, from dimensional analysis, let's say N is dimensionless, so A is basically this one basically the unit is atom. So then divided by atoms per mole. And then divided by Vc is in meter cubic, let's say like this. So what we have is the mole per, the atomic weight itself, yeah, this is the atoms, and this is atomic weight is in chemistry, or anyone remember? It is, if I'm not mistaken, it is the number of the kilogram per mole, right? The kilogram per mole. The atomic number A here, this is in gram, yeah, gram per mole or kilogram per mole, gram per mole or something like that, or kilogram per mole. So if you see here, this will cancel each other, this will cancel each other, and what we will have is something in the dimension of kilogram it could be kilogram or gram, kilogram per meter cubic. Okay, so the dimension of rho is mass per unit volume, mass per L cubic. L is length. Okay, the atomic weight is how many grams per mole. Since it is in per mole, we have to find how many gram per atom. To find the how many gram or kilogram per atom, we have to divide the A with the Avogadro's number. And then we divide the volume per unit cell. Clear, yeah? This theory, yeah? I hope everyone understand, yeah? This formula. So an example is given here. For example, we have chromium, which has BCC, which has a body center cube cubic structure. In BCC, the atomic number, atomic weight is known, 52 gram per mole. The radius is also given, 0.125 nanometer. The number is 2, yeah, BCC, since there's a single atom at the center, and we have 8 atoms at the corner, and each atom is shared by 8 unit cells. So 8 times 1/8 is 1. 1 plus 1 is 2. Total atom per unit cell is 2. The radius is 0.125 nanometer. So the lattice can be calculated from the radius of the atom using this number, because in BCC, the atom touch each other in the cubic diagonal. Okay, in the cubic diagonal. So A equals to 4R divided by square root of 3, which is 0.2887 nanometer. So the volume per unit cell will be this cubic, 0.2887 cubic nanometer. Then atom per unit cell is 2. The atomic weight is 52 gram per mole. We divide by the Avogadro's number, 6.023 times 10 to the power of 23 atoms per mole. And we will obtain, be careful with the unit, yeah. The rho theoretical is 7.18 gram per centimeter cubic. Yeah, this is the density calculated based on the atomic structure or the crystalline structure. But in actual, it is actually a little bit denser. It is 7.19 gram per centimeter cubic. Can you explain why? Anyone? Any idea why? That the actual density is slightly different compared to theoretical density. Anyone? Okay, if no answer, then I will not give the answer. So you have to find yourself. It might come out during quiz or final exam. Okay. Okay, so the densities of material classes, these are the comparison here. I think maybe we have shown this graph in the first chapter, yeah, in the earlier presentation in the first week. So in general, the density of metals is usually larger than ceramics. And then the density of ceramics is larger than polymer. So polymer is the least dense of these three materials. Composite can vary, yeah, as we have discussed a little bit about composite. A composite can be made from combination of metals with polymers, metal with ceramics, ceramics with polymers, etc. Why is metal more dense compared to ceramics? Because metal usually have close packing due to their metallic bonding. And often the element itself has large atomic masses. Ceramics, on the other hand, has less dense packing because it consists of lighter elements like silicon, oxygen, those things. Yeah? While metals is heavier element, tin, zinc, titanium, aluminum, gold, iron, etc. Polymers have the lowest packing dense because it is usually not crystalline, not in the crystalline state, but rather or semi-crystalline or even amorphous. Yeah, and usually polymers consist of the lighter elements: carbon, hydrogen, and oxygen. Composite, on the other hand, have intermediate values because they are made from combination of the other three more traditional material. Okay. So here we can see the comparison based on the table in the chapter 1 of this textbook, yeah, the Callister. So crystals are basically the building blocks of material, especially when they are made from metals and ceramics. And some engineering application requires the use of single crystals, means that then the periodicity lies even up to meter long. Yeah, so but most of materials, it's very difficult to make them into a single crystal. For example, let's say one single pen like this, it's very difficult to make all of them. I say this is made from iron, yeah, just for the sake of discussion. It's not that easy to make them all from a single crystal iron, for example. Usually they are made from multiple crystalline, what we call as polycrystalline of iron. But sometimes some applications require that the whole material is made of a single crystal, like this turbine blades, in order that there are no fracture, there are no imperfection, because which is mostly due to the boundary between the different crystals. Then it means these turbine blades have to be made with a single crystalline structure. It is not easy. That's why they are expensive. So diamond single crystal for abrasive, single diamond is usually used for abrasive. And in material science, that is why that the properties of the crystalline materials are often related to the crystal structure. Yeah, so this is different from the perspective of chemistry. In perspective of chemistry, mostly we are dealing only with the smaller size of the material, which is in the molecular level. In the molecular level, then the properties are decided by the binding between the atoms and the intermolecular binding. But when we deal with material science, which is mostly about solid state material, how these molecules or these atoms are arranged to each other. Do they have long range periodicity, which we call as crystal, or they have single crystal, or they have polycrystalline structure? And if it is polycrystalline, with what orientation are each crystal oriented towards one another? Or are they amorphous? Amorphous means they do not have any periodicity at all. So this determines the whole material properties. So not only the chemical properties of the elements or of the molecules that make that material, but also how the molecules are arranged to each other to make the bulk of the material. Okay, this is the different paradigm in material science if you compare with chemistry. So maybe some of you asking, why do we need to learn about materials, this material biomaterials again? While actually some of these we are repeating some topics from chemistry, but there are differences. Usually chemistry, they are more concerned after they discuss the molecules, and then they are more concerned with the liquid state or gaseous state. In material science, we are concerned with the solid state of the material. Okay, in this case, the periodicity of the arrangement of the molecules or atoms is important. Do they make crystals? If they make crystals, is it long range order, single crystalline, or is it polycrystalline, or do they not have any periodicity at all, amorphous? Okay. So example is like quartz fracture, the silicon dioxide, the silicon dioxide. Quartz fractures more easily along some crystal planes than others. So the crystal plane that will determine at which direction they will break. For example, once I had been working in the past during my PhD using silicon. I was using silicon to build electronic devices. Silicon also, you can break along certain crystalline plane easily, like that. But you cannot break along the other plane. Yeah, so depending on the crystal orientation, the plane that. So when you break at that plane, you will have completely smooth line at the breaking, at the fracture. Compare if you break in the random orientation. So that is because of the crystalline state of the material. So yeah, this I have just mentioned about polycrystal. So most engineering material are crystal. It is not easy. It's very difficult to have, for example, this block of material completely consists of a single crystalline structure. Yeah, most of them usually is made with this grain. Yeah, this grain in this particular picture is drawn with in different color. Grain means the single crystal, but in polycrystalline material. So single crystal located with other single crystal and they become polycrystal. And usually we call each of the crystal as grain and the boundary between them as the grain boundary. Okay, in the middle, the crystal has what do you call it? Tubular shape orientation, tubular shape. In the middle is completely vertically oriented, but a little bit in the right and to the left, it becomes more towards the side direction. But at the side, at the edges, you see that there are transformation from tubular shape into globular shape, more of round and particle-like structure here. So in these edges, the crystal shape is the periodicity is become shorter, so the crystal size becomes smaller, yeah, and they become globular. Well, in the middle, they are more of tubular and long shape of crystal. This is what we call as anisotropic material. Anisotropic means that in this case, especially in this middle, because when we have a tubular shape crystal like this, it means the crystal has longer size in one axis compared to the other size, one length compared to then we have length and width. But in globular, we call it isotropic. Yeah, here isotropic because it is more of has the same growth in all direction, in all axes. That's why it looks like a ball, like a globular shaped material. So this is an example of niobium, hafnium tungsten plate made with electron beam welding. So each grain means this is a single color. Yeah, the boundary is not clearly. Yeah, the single color is a single crystal. If grains are randomly oriented, like this, we call it isotropic. It means that overall component properties are not directional. Are not directional means that they have the same component properties in all directions. The density, the Young's modulus, yeah, all these mechanical properties that we will be learning in the next chapters. The grain size typical range from 1 nanometer, this very small one here, to 2 centimeter when it is close to the middle. From a few to millions of atomic layers. Okay, but the one in the middle or the one like here, it has different orientation, right? In one direction compared to another direction. We call that kind of crystal as anisotropic. Iso means the same. Like tropic means the direction. Isotropic. So isotropic is when they have the same property in all directions. Anisotropic means not isotropic. Maybe the Young's modulus will be larger in one crystal direction compared to the other crystal direction. Okay. What is the difference then between single and polycrystals? So in single crystals, usually the properties will vary with direction because within a single crystal itself, we have different crystal orientation or direction depending on the crystal structure. Yeah, FCC, let's say in FCC, for example, the 111 direction will have different. In the cube diagonal, the atom is attaching to each other, but in, for example, 110 direction, 110 direction in the side diagonal, sorry, in FCC, yeah, the FCC at 111, the atoms are touching each other, and in 110, the atoms are touching each other, while in 111, they have space between the atoms. So then, this will make the different mechanical property in the different direction of the crystal. That is why we call it. It has this anisotropic material property. Yeah, example is the modulus of elasticity E in body center cube in iron. The E in diagonal here in cube diagonal in 111 direction maybe 270 gigapascal. Compared to the H, in H is 100 direction. Okay, it has only 125 gigapascal. Why in the cube diagonal has larger Young's modulus? Yeah, of course, it is understandable because the atoms are more densely packed in this direction. They are touching each other. They have, then that's why it is more difficult to break them. It has higher rigidity. Young's modulus represents rigidity. Well, at the edge there is space between the atoms. It is softer. It is more flexible. Polycrystalline, on the other hand, the properties may sometimes can vary with direction, but may not also vary with direction, depending on the crystal orientation and the shape. If the grains are randomly oriented, then they become isotropic like this. So more or less, it's like a globular or shape, and then different orientation one another, but as a whole they become isotropic. So here the Young's modulus of polycrystalline iron is 210 gigapascal. But if the grains are textured like this, so here the grains is oriented more towards the side, towards the horizontal direction compared to the vertical direction. Then they become anisotropic. So the property of the Young's modulus, for example, will be different in the horizontal direction compared to the vertical direction. Okay, another property in crystal structure is what we got in material is polymorphism or allotropy. This is what I think Andy and Angeli mentioned last week with the group discussion that time about they put graphene, yeah. Although that time they could not answer properly what allotropy is. Allotropy is basically polymorphism. Polymorphism is you have the same chemical formula of that material, yeah, either in Andy's and Angeli's case it was carbon, right? But in their case it was graphene. Graphene is a single layer of carbon where one atom, a carbon is a bond to other three atoms. So then they have the 2 electrons free hanging, yeah, so that becomes the free charge carrier. This is different if you compare with diamond. Diamond, the atoms, one single atoms are exactly bound to 4 other atoms in tetrahedral configuration, which make them very strong. But on the other hand, they become also insulative, yeah, not that electrically conductive. Graphite is basically stacking of graphene. Okay, graphite is still conductive, but also not as conductive as graphene. So these are allotropies. So it means they are carbon-based material. Yeah, we don't say compound, but material, because they are made of just single element, which is carbon, but they have different structure. Diamond is tetrahedral, carbon or graphite or graphene are more of sheet-like material, a single 2-dimensional material. And this allotropy or polymorphism does not occur only in carbon. It occurs also, for example, titanium in many metals. Titanium has 2 phases, alpha and beta, and each of these phases has different structure. Iron has many different phases. Yeah, each phase has different structure depending on the pressure and temperature condition. For example, if you melt iron, then you solidify it at around 1538 degrees. First, they become delta iron, which has BCC structure, body center cube structure. Then you lower down the temperature further, yeah, into lower than 1394 degrees. Then they become gamma iron, which has the face center cube structure. If you lower further, solidify further to lower than 912 degrees Celsius, then they become BCC again, which is called as alpha iron. Okay, so by knowing this property that the allotropy and polymorphism, we as biomaterial engineer, this particular subject we call biomedical engineer, then the one of reference is biomaterial engineer, we can engineer the appropriate process such that then we can obtain the correct material having the correct structure for particular application. Yeah, or each of these has different properties because the structure is, their structures are also different. Remember at the very first lecture that in material science, the paradigm is first we have to define the processing to determine the processing, and the processing to determine the structure. From the structure, we obtain the property, and property then we can get the correct performance. During an application, engineering application, of course, you start from the end. For what application do you want to make the device for? Yeah, then what performance do you require? From that performance, you define the properties of the material that you need. And then from that properties, then you look for the correct material with the correct structure. From that, then you know what processing you need to make such structure. Any questions so far? No. So this we have basically discussed about point coordinates. Yeah. So coordinates are defined according to the lattice constant, yeah, A, B, C in X, Y, Z axis respectively. So if the position is A over 2, B over 2, C over 2, then coordinate is written as 1 half half half. At the corner, then it will be 1 1 1. So integer multiple of lattice constant basically indicate identical position in another unit cell. This also we have discussed, yeah, crystallographic direction put within square brackets, yeah, without commas, like this. So this one, the red one will be, it is in the -1 direction, X, then in the plus direction of Y, plus direction of Z, so -1 1 1. We write it as this one, and within square bracket 1 over bar 1 1, where over bar represent the negative index. Then 1 0 1, the blue one here is 1 in the X direction, half in the 0 in the Y direction, and half in the Z direction. So it is represented as 1 0 half, but then we have to make it as integer. We multiply by 2, becomes 2 0 1. This direction then becomes within square brackets 2 0 1 direction. And families of direction is indicated within this this kind of bracket, yeah, elbow bracket or something. Planes also we have studied, so I will not discuss it in any more detail. Yeah, we have done some of this exercise, yeah, of Miller indexes, and family of planes are indicated or shown as numbers within curly brackets. So summary of crystalline solids, yeah. Atoms may assemble into crystalline or amorphous structure. Yeah. The common metallic structures are FCC, face center cube, BCC, body center cube, and HCP, hexagonal close pack. Coordination number and atomic packing factor, EPF, are the same for both FCC and HCP crystal structure. Only the number of atoms per unit cell is different. So based on this crystalline structure, we can theoretically predict the density. As if we know the atomic weight usually is given in the periodic table. Atomic radius also given in the periodic table. And then the crystal geometry. And we have learned also about crystallographic points, direction, and planes. Crystallographic direction and planes will be related to atomic linear density and planar density, although we haven't discussed this in detail. Yeah, we have discussed the volume density. But linear density means the density of the atom in one single line. Planar density in one single plane. Materials can be single crystals or polycrystalline. Single crystal if they have long range periodicity. So one whole block material, just single crystal, very long range periodicity. Polycrystalline if shorter range periodicity, and then they different crystal are are located adjacent to each other, neighboring to each other, and this will determine also the properties of that material. And usually, in within single crystal, the property will differ also in their orientation, what we call is isotropic, but are generally non-directional. If they are isotropic in polycrystal, if it is grain, if it is globular shape, with randomly oriented grains. And some materials can have more than one single crystal structure. This is what we call as allotropy or polymorphism. Okay, any questions so far regarding crystalline solids? From you?
Sir,
Yeah.
I'm just curious about graphene. So why does graphene is not widely used until now? Like,
Graphene.
yeah, graphene.
So Andis and Angelis material that time.
Yeah.
Yeah. Why graphenes are not widely used? What do you think it should be used for, based on your knowledge?
Can be used for, I think, medical use too. I don't know, but the properties of graphene is a promising properties, right?
Which property do you find it promising for biomedical application?
I've searched for, so it is said that it can be used for to accelerate the osteogenetic differentiation of human mesenchymal cell, stem cell, and others. But is it so hard to make graphene, or?
Yeah. Okay. To answer your question, yeah, depends. Yeah, hard or not hard, hard or easy to make graphene. It is not that easy. It is not easy. Yeah. So it could be simpler, but it could be also difficult. What do I mean with that? So when it is first discovered or invented, let's say, they make it from graphite. From graphite, and graphite, we know that it is widely available in pencils. Yeah. So what the Nobelist winner, Nobel Prize laureate at the time from Manchester University, Novoselov and Game, both are basically Russian-born physicists. They put this graphite and then they use adhesive tape, Scotch tape. You know Scotch tape. They just put it like on the graphite of the pencil and then put it like that and then peel the Scotch tape, and they have one single layer of graphite, which we call it as graphene, on that Scotch tape. And then they characterize and they find different marvelous properties of graphene, which among others in very high thermal conductivity, electrical conductivity, etc. But that's for science. So for application, industrial application, then you need to produce it in mass scale, right? And this is not easy. So and then when you produce them in mass scale, of course, we call it as graphene flakes. So when they are, how to maintain, for example, them as two-dimensional layer, properly oriented two-dimensional layer, rather than, because when they start to stack each other, then they become again a simple graphite or just stacks of graphene. Yeah. So in one way it is easy to make, another way it is not that easy. And one of the way to fabricate graphene is you produce graphite. From graphite you produce you have to use this kind of process. I forgot the name, which you produce first graphene oxide, GO. We call it graphene. It is graphene, but with bonding, with the dangling bond of oxygen in both upper and bottom layer of the graphene layer, and then you have to reduce it. The reduction process usually require the use of very strong acid. This makes also another complication. It means the processing is not environmentally friendly, and so to make them in mass production is also not easy. Of course, yeah. Recently there have been many research. Try to make graphene from graphene oxide, so making them first to become reduced graphene oxide. With it more environmentally friendly processes. Yeah, but it is not widely yet available. But there are more and more industry and research on that. So to say that there are not yet application of graphene, yes and no. So yes, yeah, it is not, of course, not as widely applied like is copper or iron, but there are already some growing application of that. I know a friend of mine in Thailand. He's the head of the National Center for Microelectronics in Thailand. He used graphene already for making imprinting graphene for making many biomedical devices, making sensors, etc. In fact, if you search of my publications, in recent publication also, I use graphene for developing ECG electrode. Yeah, the graphene is coated onto cotton substrate. Yeah, you can search some recent publication by me, and I went with my PhD student in UTM, Malaysia. So it is already applied, but not in too many applications yet. Yeah, it means there are still rooms for more research if you are interested. So as you mentioned about to stimulate growth of mesenchymal cell, that will be interesting. It will be interesting. And if we look at its brother material, brother, so the same allotrope of carbon, let's say carbon nanotube. Even carbon nanotube also not that widely implemented yet, yeah, as a engineering material. It is invented or discovered, yeah, earlier than graphene in the late 1990s by Iijima Sensei from Japan. And carbon nanotube, it has basically carbon nanotube is graphene material which is being folded to make tube. It is also good. It has many good material property, mechanical as well as electrical, but not yet that widely available because it is also more difficult to fabricate with a constant or properties. Yeah. So that is in material science, especially with this new advanced material made from nanotechnology, graphene, carbon nanotube, and many other new materials. They are still in the research stage, I can say like that. Is this in contrast if we compare with iron, for example? Iron is already discovered or invented much in the ancient world, right? They already used iron. And then what they do now is to make a research for lighter iron and then make different kind of alloy with different kind of metals. Yeah, that will be my comment on your question. I'm not sure if that answers your question. Yes, sir.
Yeah, thank you, sir, for the answer. Yeah, karena I saw the YouTube video and I think one England in England one company already made yeah large production of using graphene, but nggak banyak kayak gitu, sir. Not many companies.
Yeah, I think the company is a spin-off from Manchester University because they are the leader now in the world for graphene. They are the one that discovered graphene, the group of Professor Novoselov. And from there, they spin off the company to fabricate and produce graphene. But not yet implemented in many industries. They developed the synthesis, the processes to make it more mass produced, but its application requires more research.
Okay.
Okay.
Thank you, sir.
Yeah, you're welcome. Let's take an example of calculating planar density in crystalline solid. Okay. In iron, in 100 and 111 plane. Calculate the planar density for each of these plane. So, for example, here this is in less than 912 degrees Celsius. Iron has BCC structure. Yeah, this kind of thing. So in the 100 plane, it will be in this plane. Okay, so in two-dimensional plane. So in that case, then the A will be equal, since then this is in BCC, a body center cube. You remember body center cube, the atoms touch at the cube diagonal. So here the A is equals to the 4/3 times the square root of 3 times R. And the radius of iron is known, usually from the atomic periodic table, 0.1241 nanometer. So the planar density at this 100 plane will be the number of atom divided by the area. The area is a square. A square. So we have 1/1 atom, because here there are 4 atoms located at the corners, okay, at the corner, but each of these atoms is shared by 4 others 2D repeating unit. Okay, so that is why 4 times 1/4 equals to 1. So that's why this atom repeating unit is 1 divided by a square. A square, we substitute with this value, 4 square root of 3 divided by 3 times R being squared, and we will find 12.1 atoms per nanometer square. Or if we change into square meter, it will be 1.2 times 10 to the power of 19 atoms per square meter. In 111, this is a little bit more difficult. In the BCC atom, body center cube atom, so the 111 plane will be like this. Okay, will be like this. So if you see it, then this is the atom. The red one is atom above the plane. The atoms on the plane is this green ones. Yeah, the green ones is the atoms in the plane. The atom below the plane is this one. Yeah, the light cyan. So this one, in this case, the height here is this one. Yeah? And this is equals to the square root of 3/2 times A. So the area becomes, the area is square root of 2 times A times H of that plane. Then it equals to, so then we replace this, we substitute with this into H, and we obtain square root of 3 times A square. And then when we substitute again the value of A with the R for BCC, which is 4 square root of 3 divided by 3 times R and mean square. So this is what the values that we obtain. And the planar density for atoms per repeating unit like this, for one single plane here, there are 3 atoms at the corner, but sorry, this is the repeating unit, yeah, not a triangle, but instead it is parallelepiped. Yeah, parallelepiped. We have here, it is shared by, if we add each other these 4 corners, it basically will become also one single atom per this 2D repeating unit. Okay. Then divided by the area, which is this one. So we obtain 7 atoms per nanometer square. So you see that at the 100, it has denser atoms per square area compared to in the 111 plane. Okay, in the 111 plane, it's not that many. Okay. And how do people know? How do researchers, scientists, or engineers know whether a material has what crystal orientation? So what they use is a technique called as the X-ray diffraction. So first is what is X-ray? X-ray is basically a type of electromagnetic radiation, which is very has a very short wavelength. Yeah, here is the range of the X-rays wavelength from around 1 micrometer until about this is then several less than even 1 nanometer. Yeah? 1 micrometer, less than 1 nanometer. So if you compare with visible light is somewhere here in this region, the wavelength. So visible light has about 632 nanometer, this 700 nanometer in the red type. In the blue region is around 400 nanometer. X-rays can go less than that. The wavelength. The frequency is the opposite. So X-ray has a larger frequency, electromagnetic frequency compared to visible light. And using X-ray, we use diffraction grating. So diffraction grating must have spacing comparable to the wavelength of the diffracted radiation. It cannot resolve spacing less than the lambda. Since the spacing between atoms and in crystalline structure is in the angstrom region, okay, in nanometer region, so we have to use X-ray. We cannot use visible light diffraction to elucidate the structure of solid, crystalline solid. So spacing here in this crystalline solid case, it will be the distance between the parallel planes of atoms. So therefore, this is how the researchers are using X-ray to determine the crystal structure. They use X-ray with certain angle, and usually this angle can be varied. Will be varied from 0 until certain angle. Whenever the diffraction occurs, which will be indicated by this kind of peak, that angle will be corresponding to the D, yeah, the spacing between the planes of that crystalline solid. That is incoming X-ray 1, incoming X-ray 2, then outgoing X-ray 1, X-ray outgoing X-ray 2. And if they reinforce each other, means they are of the same phase. Okay, so they remember from physics. They will reinforce, the wave becomes stronger, the amplitude. Reflection must be in phase for a detectable signal, but if they're not in phase or out of phase, they will be weakened, the amplitude. So by measuring this critical angle of theta c, we can calculate the computation or the plan of the spacing between the plane and that crystalline solid structure. Okay. This is an example of X-ray diffraction pattern for polycrystalline alpha iron, which has body center cube structure. So the theta c, it will have peak in 110, sorry, not 110, 110 plane, 200 plane, and 211 plane. Okay. If the material is amorphous, you cannot have peak like this. Usually it will be very like this, yeah, just random pattern. Yeah. If it is not crystalline, if it is amorphous, just very random, you will have like this. So you know that you have a crystalline state material if your X-ray diffraction pattern has peaks. in this in the intensity to diffraction angle graph. And if you have one peak, it means it has the diffraction angle, because if this is polycrystalline, right? This is with different orientation. When the crystal the X-ray hits that material in one of the grain, it will be diffracted in by the 110 plane, in the other grain 200 plane, the other grain 211 plane. That's why we have this 110, 200 to 111. Okay, so this is 110, remember? 200, it means every single unit cell, it repeats itself twice at the x-axis, yeah, 200. This is 211. Okay, I think the summary is similar to the previous slide. Okay, if